Hello, I'm Aaron Sloman. I'm at the School of Computer Science in the University of Birmingham in the UK, and I've been asked to give a talk on artificial and natural intelligence for the Sharif Spring School. I'm going to make use of this webpage, which is online and will be available there. The organisers will be able to provide these links. But I should also use videos. This gives you a chance to see what I look like. Not that that's very important, but most of the time you won't see me because it's not necessary for this presentation. Instead, I shall show you this little girl. She's about a year and a half old. She had been playing with a pencil, scribbling on bits of paper over here, and then started crawling along the carpet holding that pencil, and she saw this sheet of paper lying on the floor, and I happened to notice she was coming, and I had a poor quality video camera, so I thought I'd start recording it. And this is what I found. This is slowed down about a third of the speed. She pushed the pencil through the hole. Then she pulled it out again. Then she did several things in parallel. She turned the paper over. She moved the pencil round to a new position. She rotated the pencil. She moved her head and eyes in order to see what was going on the other side. Pushed the pencil in. Then brought it back to the original side and pushed it in. And you might want to see that again, so I'll just put it back and let it go a bit faster. So she pushes it in, pulls it back, and the remarkable next thing is that she does several things in parallel, but with very good precision, considering how young she is. And at the end, she just left it and did something else. She wasn't looking for applause or anything. The moral I draw from this is that this young child has a very rich spatial representation of things in the environment, including representations that provide information about possibilities that could be realized but have not been. And in particular, there's the possibility of pushing the pencil through the hole, which she realizes, and then the much more sophisticated possibility of moving the pencil round to go through the same hole in the opposite direction. I don't think there's any robot on the planet that could come up with that idea and then do it as she did. So we'll leave that for now. It makes the point that there are deep issues in natural language, in natural intelligence, that are not understood. There's one other point to be made, that somehow she had a lot of knowledge about what was in the environment, what she was going to do, and how to do it. That knowledge involved a very rich structure of objects, parts of objects, for instance the hole in the paper, the relationships between objects. So for that she must have had an internal language which was much richer than the language she was able to use to communicate. And I suspect that that's true not only of this little toddler, but of all toddlers. But not only that, but of all intelligent animals that can deal with spatial configurations, like squirrels, nest-building birds, elephants, monkeys, porpoises, and many others. So we'll put her out of the way now, and I'll come back and say something more about what I want to talk about. So there's a lot of work in artificial intelligence, and I think it misses out on some very important aspects of natural intelligence which are just ignored, and therefore the things that are achieved are in some ways much simpler and more shallow than what a young child like that does, or a bird building a nest does. Let me show you a bird building a nest. This is a BBC program on YouTube about weaver birds which make nests like that. But when they start, the males who make these nests mostly don't really know how to do it. And you'll see a young male in a minute who's got, there he is, he's got a long leaf. He's now moved somewhere else. And with that leaf, he's going to make a knot, or he hopes to make a knot, to tie it onto this twig. Makes a couple of loops, and then he very cleverly gets hold of the end of the end, but forgets to hold on. So when he comes round, there's nothing there for him to push it through. He's got to start all over again. Well, I don't know how that particular male managed in the end, but you can see other things happening. There's something that's got a rather more structure. That's a later stage, presumably. This shows you what happens at a later stage when someone can get inside the nest and do things to it. I don't know whether that's the female who's just preparing it for her preferences. Anyway, I will leave weaver birds. Again, there's nothing in AI that's remotely like the understanding of spatial structures and possibilities that a weaver bird has. At least there isn't at the moment that I know of. Now, I think that there are a number of different issues that I want to address here. One is that there are deep links between artificial intelligence and philosophy. Philosophy is sometimes thought of as a rather narrow and perhaps in some cases a rather sterile discussion. But I see philosophy as having very deep connections with science. Both of them try to understand the universe. Both ask questions about what is possible and what makes it possible and why some things are impossible. The difference is that after a while science starts getting fairly precise answers and gets them in a form in which you can start doing things, including using the knowledge for engineering purposes. Whereas philosophy goes on with the problems that can't be addressed in that way, although it may come up with new problems. And it can spawn science as the philosophy becomes better developed. Anyway, philosophy of the sort that I'm talking about is concerned with trying to understand what sorts of things are possible, and I think science is also trying to understand what sorts of things are possible and how they're possible. Now, I started off being interested in this kind of thing initially when I was doing, first of all, mathematics, and then I got interested in philosophy, and I found that some philosophy students that I was friendly with said things about mathematics that I thought were wrong. And then I read that there was a philosopher called Immanuel Kant who had said things that I thought were right. They corresponded to my views on what I was doing when I did mathematics. But this is around about 1959 or 60. All the philosophers thought that Kant had been refuted because Einstein had produced a general theory of relativity saying that space was not Euclidean, and Eddington had collected evidence in support of that by using a solar eclipse in 1919, which showed a star in a photograph being seen in a slightly different place from where it would normally be when the sun is not eclipsed and the star is far away, not blinded by the sun. So that showed that the light from the star had been bent coming near the sun. Anyway, although that showed that space was Euclidean, it was not Euclidean, it left most of Euclid's elements in which he had a lot of axioms and theorems and postulates and constructions. It left most of it intact, except for the parallel axiom. But even the parallel axiom is something that we can think about as being applicable on a plane. The parallel axiom says if you have a straight line and then in a plane, and then another point in the plane that's not on the line, then there's exactly one straight line through that point that no matter how long it goes on, never intersects the other straight line. Anyway, the fact that there are geometries that are different, like the surface of a ball or the surface of a donut, doesn't affect the fact that there are things about Euclidean geometry, and the ancient mathematicians discovered them and proved quite deep theorems about them. and I'll come back to that. So the question is, what were their brains doing? Now, one of the important things about these mathematical discoveries is that they're not just observations about what does or doesn't happen, like you might say, well, sometimes the sun shines and sometimes it doesn't, and sometimes there are flowers growing and sometimes they're not. The discoveries made in mathematics are about things that are impossible or things that are necessarily the case. I mentioned an impossibility earlier, namely two straight lines in a plane bounding a finite surface, or three planes bounding a finite volume. That's not possible. But there are many other impossibilities. For instance, moving from, if you have a closed curve in a plane, in a plane surface, closed curve, then if there's a point inside the closed curve and another point outside, there's no way you can find a path through the plane from the first point to the second point without somewhere touching the closed curve. Well, that's just one among many examples of theorems in geometry topology that are not refuted by anything that Einstein did. Anyway, let's move on now. This web file has a lot more detail, and I'm going to skip a lot and just focus on a few things. One of the things I'll just mention that I'm not going to talk about is that our project at Birmingham has had a lot of investigation of things like emotions and motivation and moods and preferences and so on. That's usually referred to as affect, and there's information about that here for anyone who's interested, although that work has temporarily been paused. I also, related to that, want to point out that there are many theorists in psychology, AI, neuroscience who think that motivation has to be related to rewards. And so they think that intelligent robots will have to have some rewards, and they'll have to choose what to do on the basis of what brings the rewards. And I think that is really completely false. That baby with a pen wasn't trying to get any kind of reward. She just had an idea that something could be done and then wanted to do it. A child walking along the road might notice something in front of him on the road, like a tin can, and then get the motive to kick it, and he'll kick it. It doesn't have to be rewarding. And I think there are very deep reasons for this, that evolution discovered that if various situations trigger motives, then young learners can work out ways, try ways of achieving those motives and learn things from their successes and failures, which will be stored and may become useful later on. And they don't have to have any knowledge of why they're doing it as long as they do it. And if they do enough of it, they'll pick up a lot of knowledge, and that's the reason why it's good for them to do it. But that wasn't their motive, because they didn't know they were going to get knowledge from twisting things, pulling things, pushing things, throwing their food on the floor, and so on. They just are triggered by these deep motivations, which I call architecture-based motivations. So a lot of intelligence is concerned with architecture-based motivation that suggests a possibility that might be realized, and then intelligence is used in realizing it, like that child. I got into artificial intelligence about 6 or 7 years after finishing my PhD, which was defending Kant's view of mathematics at Oxford. I was a young lecturer at Sussex University, and an AI researcher called Max Clues came to Sussex University in 1969, and there's more information about him here if you want to find out more. He was very inspiring. Unfortunately, he died quite young in 1981. But he got me going into programming and artificial intelligence and persuaded me to submit a paper to a conference in 1971 in which I commented on a very important paper by McCarthy and Hayes in which they gave a manifesto for logic-based AI. And when I read it, I thought that, although it was very interesting and very deep, there was something wrong insofar as they didn't allow for the kinds of reasoning that I personally, as a young mathematician, had found most useful, namely diagrammatic reasoning, which is very different from the logical reasoning. And they were claiming that logical reasoning, logic-based reasoning, is adequate for everything, for an intelligent agent, and including being heuristically adequate. That's to say, you don't waste time searching around in an impossible context if you use logic. And I think if you're trying to solve some of the old geometric problems, you would waste a lot of time if you try to do it all in logic. Whereas if you have diagrams, whether they're on paper or in your mind, you're doing something very different from reasoning with logic. Anyway, that was what my paper was about, and as a result of that I got invited to spend a year in Edinburgh learning about AI in one of the leading AI centres. So I was very lucky. I managed to get a chance to learn about programming and artificial intelligence from some very bright people, leading AI researchers. And I thought I would set myself the goal of trying to find out how to use AI to build a baby robot that would have the sorts of motives that I was talking about earlier, to try things out, and would eventually grow up able to make mathematical discoveries like Euclid and Zeno and Archimedes, just because he's highly motivated, he, she or it, the robot is highly motivated to do that sort of thing, not because there'll be any rewards or anything of that sort. And I still don't know how to program a robot to develop those abilities, and I don't think anybody else does either. And the rest of this talk will be about some of the features of human spatial intelligence and why it might be difficult to implement on a computer with a digital processor, where everything's represented in switches that are on or off. Well, there's an awful lot going on in brains, and I'm skipping quite a lot of stuff here. I want to now go to a strategy for trying to make progress with this project of finding out what brains are doing, and if they're using chemistry, as I suspect they are, how one might get clues as to what's actually going on. And this work, some of this work was done with Dr. Jackie Chappell, who's a biologist at Birmingham University. She studies animal cognition. And some of her work was concerned with a crow called Betty, from New Caledonia, a New Caledonian crow called Betty. After Jackie's work, another research student in Oxford used the crow to perform some tasks which involved getting a bucket out of a vertical glass tube. And Betty couldn't reach the handle, and worked out for herself that a piece of straight wire lying on the table could be used to make a hook. And in fact she made hooks in several different ways, which I later discovered by looking at the videos in the Oxford Ecology Lab. I won't talk about the different ways she made hooks. The point is merely that just because she found a way of making a hook that worked, she wasn't satisfied, and that may again be an example of architecture-based motivation, not reward-based motivation, but I don't know. Now, the main point about this thing is that Betty comes very late in evolution, and in between there are all sorts of intermediate cases where there are very simple, perhaps single-celled organisms, then more complex ones with more internal functions and more capabilities. Some of them even have little things that they can wiggle to move, and that may be useful because if there's something dangerous in the surrounding liquid, then if you wiggle you might be able to move to a place where it's not so dangerous. Or if the level of nourishment that you need from the surrounding water is too low, if there are sensors in the skin, then it can wiggle and see if that changes the level of nourishment by moving it to another place. And then other things that would get more complicated, and with their more complicated structures they can do more complicated things, but they also have more complicated needs for food and shelter and so on, but also more complicated information processing to control what they can do. If this thing can't do anything at all but just stay where it is and And this one perhaps can decide whether to let molecules in, which are good, and keep molecules out, which are bad, and on that basis grow and then eventually reproduce. It's got some kind of information about which molecules are in contact with its skin and where they are. That's information processing. But in that case, it'll all be done with chemistry. It hasn't got a brain. Neither will this thing have a brain. This may have a very simple brain. Betty's definitely got a brain. So there are all kinds of different forms of control, all of which depend on acquiring and using information about the environment, information about the current state of the organism, what it needs, what it doesn't need, and so on. And though the information is used in increasingly complex ways to do things, to control actions, or perhaps to reason about a possible event in the future where an opportunity might be available, although that's not necessarily something that will be done by an organism like this. Humans, of course, do very elaborate planning long time in advance in large teams, but some of that now depends on the use of computers, and they couldn't have done that a few thousand years ago when they had much simpler kinds of planning capabilities, let alone simpler tools for drilling and manufacturing things. Anyway, so I'm leading up to a theory about how evolution produces some of these abilities, and it was developed in collaboration with Jackie Chappell, and the theory is, I'm leaving out some of the details, that human and other animal genomes have a feature which we call which makes us call them meta-configured genomes. What this means is that a genome doesn't just specify everything that's to be done at the start of the life of an organism and then how all the things that are created internally will go on developing. It may do different things at different stages of development, including starting to grow new things at certain stages. That should be very obvious from, for instance, the genetic effects of sexual development in humans. There are lots of physical changes and motivational changes and changes in interest that occur quite late in life, and if they occurred in newborn babies, that would be a complete waste of time. But that's just one example of staggered gene expression. And I think there's a lot more of it going on in different stages, and I'll try to illustrate that with this diagram. The idea is that you have this genetic structure which is up here, and this is capable of producing something in the developing organism, and just producing different things at different times. And what it does at early stages produces changes internally, and then there might be behaviors that affect the environment, and there might be sensors which get information from the environment after these simple behaviors, perhaps like the ones that I mentioned earlier with little microbes wiggling around. These simpler behaviors can provide information that may be stored. It may be made use of immediately, or it may just be stored because it will be useful later. Then at a later stage, something new might come out of the genome which builds some new structure or some new behavior, which generates something a bit more complicated, perhaps more abstract, and that in turn can influence simpler behaviors and organize them to influence the behavior, to influence the environment, and then there'll be sensory information which will lead to more records. And this can happen in several waves of increasingly sophisticated genetic specifications producing not directly behaviors, but producing information processing mechanisms, producing new contents, like new motives for information processing mechanisms. And when that happens, precisely how the gene is expressed may depend on the records that were previously acquired from much earlier gene expression. And the most obvious example of that is human language development, where initially the genes get a very young child to start babbling, and the child babbles, and it may listen to the talking that's going on around it, and it gets influenced in the kinds of muscular movements and these nervous control mechanisms required to produce the sounds that are in some ways related to the ones that it hears. Then later on, the genome can generate new competences and new motives to combine these sounds in more complicated ways, 2 or 3 at a time. And that can happen in the presence of adults who respond, and the child may keep records of what the responses are with these different things, and those records may stay around and be used at a later stage. Now, I don't want to go into all the details of that a theoretical linguist would, which would take up the whole lecture, but the point is that more and more complex information structures can come into records that are acquired by interacting with the environment in more and more complex ways that are produced by later, probably more recently evolved genetic structures, which may have various kinds of abstraction in them. By abstraction, what I mean is that they have details that are not provided in the genome as to what needs to be done, what should be done. Instead, some of the details are picked up from the previous records that were produced as a result of earlier gene expression. So that allows the later expression of a genome in one environment to be very different from the same expression, from the later expression in another environment of the same level of genetic structure. And that is shown very clearly in the case of languages by humans who presumably have roughly the same genome, end up talking completely different languages in different parts of the world, and they will have different stages, and at each stage they may have different sounds, different patterns of sound combinations, different syntactic structures, different semantic contents, and so on, and even different purposes for which they use a language. Now, I want to show an example of what happens when children learn languages, but learn sign languages. Okay, this is a YouTube video called The Birth of a New Sign Language in Nicaragua. Some people viewing this may already know about it. For a while, the Nicaraguans thought that deaf children should learn to lip read, because there's no use learning a sign language because the people around them who are not deaf won't be able to understand the sign language. However, learning to lip read is not at all a successful strategy, and they were persuaded by experts that they should teach the children a sign language. So they got a lot of children together, and they had a teacher, and the teacher had been born deaf and had learned sign language, and his job was to teach the students. But very strange things happened, and this is late in the video. I'm going to start it up.
It brought deaf village children into Managua to end their isolation. Here, educators tried to teach them an existing sign language. The effort failed. The children showed little interest in learning a language.
So what happened was that they started signing themselves. They invented their own language. And the teacher had no idea what was going on. There they were, waving their fingers and hands around, smiling, nodding, moving their heads. And eventually they brought in experts from MIT and other places who came and studied these children and worked out that the language they were being taught was much too limited for them, because the poor teacher who had been brought in had never learned a sophisticated sign language. So together they developed their own sign language, and in fact it grew into an independent language. The point about that is that the genome that I was showing you previously, which these children had the ability to make them start doing things which, when they were in the presence of other children who were doing similar things, caused later parts of their gene expression to interact with the results of the early ones, and gradually they were able to cooperate in creating a new sign language. But normally when a young child is developing its spoken language, although it too isn't learning but cooperating, it's in a minority because there are already a lot of other people who speak. So that child's cooperative development looks like learning because it is so constrained by the fact that it's in a minority and it's cooperating with a large dominant majority. So I'll leave that. If you search for deaf children, sign language, Nicaragua, you can find the video and watch the whole thing. It's a fascinating thing to look at. So what I'm suggesting then is what was going on in there is an example of the sort of thing Jackie and I were talking about with their meta-configured genome. Now I'm going to skip. One of the questions is whether AI will eventually catch up with natural intelligence. And some people think that by finding more powerful learning mechanisms, and in particular the current deep learning mechanisms, which are highly fashionable and doing lots of very impressive things, are thought perhaps to be capable eventually of enabling future robots which have the right physical apparatus as well as the right learning mechanisms to develop something like human intelligence. And I think that is completely wrong. There has to be different kinds of intelligence, and the kind that comes from learning statistics and then finding probabilities, which is what deep learning systems do, is very different from some of the important kinds of learning. And I'm going to try to illustrate that. I've already made the point that languages are created, not learned. So I want to now talk about the difference between what Hume and what Kant said about learning mathematics, and then I'll illustrate that in a way that is related to what I was saying about the genome not just producing statistics-based learning mechanisms, but something else. That's David Hume. This is Immanuel Kant. And Hume produced theories which were very influential, and I'm not going to go into great details of them, but the main point was that he seemed to suggest that there are only two kinds of knowledge that can be true or false, what he called matters of fact and real existence on the one hand, and relations of ideas. And the matters of fact and real existence are things you have to go and look at in the world to find out, how objects behave if you throw them, or how the sun moves at different times of the year, what happens if you mix water and sand, and so on. These are all things you can't just work out by thinking about them. You have to examine the world and perhaps perform measurements. But if you, for instance, if you know that by definition all bachelors are unmarried, then that's just a relation between the ideas of bachelor and unmarried. And a more complicated example is if you know what uncles are, then you can work out from the definition of an uncle and a bachelor and marriage that no bachelor uncle can be an only child. And I'll leave that for something to do later. No bachelor uncle can be an only child. The bachelor uncle must have a brother or sister. And you can work that out, but you can do it just by using the definitions of uncle and bachelor and child and so on. Now, Immanuel Kant said there aren't just these two kinds of knowledge. There's something else which you get in mathematics. And I can only give you a very brief idea. There are links in this document to more detailed explanations. So Kant said there are certainly some kinds of things that are analytic. That's to say, they're just relations between ideas. And then there are other things that are not, that there's something else going on. You might have to get the information from the environment, which is what Hume said. But Kant said there's something else you can do to get synthetic knowledge that isn't analytic. And that happens in mathematics. And another distinction he said was important which I don't know whether Hume made, he might have done, is the difference between things which are necessarily the case or impossible and things that are contingently the case. They are maybe true in some situations and false in others, and the necessary truths are typical of what you discover in mathematics. And I'll give you some examples. If you have a plane surface, you can draw two straight lines in it, and if they're two straight lines, no matter how big they are, they will never combine to enclose a face, an area in the plane that's of a finite size. For that you will have to add a third straight line, so that you then end up with a triangular region. So you could have a line going like that and a line going like that, or any other pair of two lines, but they would never form a finite region. They'll have a region enclosed between them, but if they diverge in this way, you'll go on forever without ever finding a boundary. So the claim is then that for a space that's bounded in all directions, you need at least three lines if the lines are all straight. And that's not something you can get just by starting from definitions of straightness and line and planar and so on. You need insight into spatial structures. And I'll give you an example of another kind of insight, which I will... a lot of the ideas I have were put into a book called The Computer Revolution in Philosophy, which was published in 1978, and it's been updated and it's online. And there are links to it on this web page. It's got a PDF version as well as HTML, and if you go into it, there are contents and so on. Yeah, that's what I wanted. If you have a blue triangle like this, you can draw a straight line that goes through one of its vertices and then goes through the opposite side. So this is a point on the triangle, this is a point on the triangle, that's a point on the triangle. This straight line goes between these 2 points and through the third point. So if you continue that straight line indefinitely, it'll go on forever. Now I want to ask you to think about what happens if you take this point and just move it further and further away along that line, the straight line. What happens to that angle? Well, I find that most people, whether they've studied Euclidean geometry or not, if I leave them to think about this for a few minutes, some people take half a minute, some people take a few minutes, they will come up with an answer which I'm not going to tell you, but you can probably work it out for yourself. So something happens to this line, this angle, if you just keep moving, stretching the triangle up that way. But furthermore, it satisfies the three conditions that Immanuel Kant had specified. In order to discover this, you don't have to go around doing experiments on triangles in different altitudes and using different colors and shapes and sizes and so on. If you think about it and you understand it right, you can discover non-empirically what the answer is. And when you've understood it, you'll see a second feature, which is that the answer is necessarily true. If this triangle had had a different shape, for instance, if I had moved this over here and then I'd chosen a different triangle, a different line going through that angle, through that point, and then I'd moved this triangle so that it started there and moved on that line, then as long as it's moving, the vertex is moving out on a line that goes through the initial vertex and between the other two lines, what happens to that angle as it goes further away will be the same. Now, so what we have here is something you can discover a priori, and furthermore, if you've understood it, you'll agree that it's necessarily the case. There cannot be exceptions if it's a planar surface. But furthermore, you can't work it out just from your definition of a triangle. You have to visualize spatial structures and relationships. So it's not analytic, like all bachelors are unmarried, or no bachelor uncle can be an only child. This is something you have to arrive at by something different from definitions and logic, using what some people call spatial intuition. And my claim is that a lot of animals, not just humans, have the kind of spatial intuition that enables them to reason about what is and is not possible in various situations, and as a result, not to try things out that would kill them, or not to try things out that would waste their time because they obviously cannot lead to the solution. Even though they may not be able to prove to themselves that a particular solution will work, they can certainly, in many cases, avoid wasting time by identifying solutions that will definitely not work. Well, I've more or less run out of time, so I'm going to have to hurry up. One of the things that I'm claiming here is that we don't know how brains do what I was just talking about here. They certainly do not use logic. You can take Euclid's axioms, express them logically, and then derive theorems. And I'm saying Euclid didn't do that, Archimedes didn't do that, Zeno didn't do that. They were doing something else, like what I was talking about here. And one of the real problems is to find out how brains do that sort of thing. Well, I've contrasted that with doing logical reasoning, which can be done easily in computers because everything is just true or false, and binary distinctions can be explored exhaustively by a computer, and even logical deductions using more complicated forms of reasoning, provided they're discrete and every formula is finite, you can do a lot of checking and you can find proofs in logic. But geometrical topological reasoning of the sort that I've been talking about and illustrated here is much harder for computers, and what we don't know is how human brains do it. Well, I don't have clear answers, except that I think it's connected to some of the things that happen when you look at spatial structures and move around. For instance, here are spatial structures moving. And notice that as the viewpoint moves, all sorts of changes are occurring between the visible portions of the surfaces in the room. Some things are becoming invisible and becoming visible again. Some of the relative angles are changing, and a huge amount of that kind of thing is going on in parallel. And if you have another much more irregular structure like a pot plant, then that's also changing in very complicated ways, all in parallel and interacting with the appearances of the chair and other parts of the room. And what I'm getting at is that brains seem to have ways of processing a lot of changing spatial relationships in parallel in ways that enable them to extract three-dimensional information. But I don't think it's precise three-dimensional information about coordinates, XYZ coordinates. It's about what's nearer, what's further, what's longer, what's shorter, what's wider, what's thinner, a lot of partial orderings. And I think that is enough for a great many ways of interacting with the world. It's not enough for playing darts well. You need precise information about distance for that. But for a great many actions, you don't. And I think there's something about the way evolution has very cleverly designed human and squirrel and crow brains that enables them to do this sort of thing and do it successfully. And in the case of humans, we were able to reflect on what we're doing and discover that some of the consequences have this mathematical property of being necessarily true, not being true by definition, not analytic, and being knowable a priori. You can just think it up and work out the solution. You don't have to go and do experiments. And so I'm saying that what Kant said was right, and if only he'd lived a couple of hundred years later, I think he would have been doing AI and trying to demonstrate how brains might do it. But there is a possibility that it can't be done by digital computers, and maybe what brains do is use chemical processes below the level of neurons, because there are millions, billions of chemicals doing all sorts of things inside the neurons, and some neuroscientists are beginning to think that there's much more going on there that's of great importance than anyone has previously realized, and perhaps they're doing something that can't be done on digital computers. And Turing himself in 1938 said that computers can match human mathematical ingenuity, but they can't match human mathematical intuition. And there's a reference to that somewhere in this thing as well. Anyway, I've run out of time. I hope that makes some sort of sense. There's a lot of information linked from this webpage, and I'm sorry that I've gone over time.